Okay, hello everyone. Let's start our lecture. So I see people are still coming. So it's important lecture today. Please take it serious. Please make sure you hear me. Please make sure you're active. Please make sure you rehear the lecture if you don't get it timely. So your homework number 7A, we call it 7A because chapter 7 will be split into parts. One will be before exam 3 and second will be until Thanksgiving and after this. So homework 7A is posted now. I sent it to you last night. And you have exactly 1 week to do it until next Wednesday. It's quite comprehensive homework, but please deposit your time on it because you need it before your exam. Your homework is due Wednesday. As always, we will have help sessions on Monday and Tuesday next week, so please attend. And this deadline will be rigorous because you need to have your solution before your exam. So I do want to post my solution to your homework 7A by the end of Wednesday next week because your exam will be on Friday. Like usual on Wednesday, I will give my own help session. So please attend. Please make sure you have it. Again, on Friday, this Friday, I will post you some materials for your exam. But this is new topic, entropy. Please take it seriously. Also, I recall ACI survey, student evaluation of instructor are open. So please evaluate me, evaluate this course, whatever it is. Yep. I know it's a difficult time and everyone want to have it in person, so please don't blame on it, but otherwise please evaluate it. Anyway, so before I start, I share my screen and a couple of people ask about homework number 6, about last problem. So let me a little bit go back to it. So in problem last, so that is about last problem. By the way, if you did not submit your homework yet, please do it. It's still open, but I do want you to switch to the now homework 7 soon and post my solution. Anyway, so what you should realize in this problem number 6. So you have heat pump. You heat your house by means of heat pump. So if you look at this picture in terms of heat pump and the screen, so what is it? What is cold source and what is hot source if you have heat pump? Your hot body in this, it will be your house, right? Here it is. Right? This is your house. And your cold body, it will be street, it will be outside. So what do you have in this problem? You know that heat goes out from your house with goes out from your house with given heat loss. Heat loss will be 80, I think 80,000 kilojoules per second, 80 kilowatt. But what your heat pump does? Your heat pump compensates these heat losses, right? Heat goes out here. So what is your Q out, QH here? It is to compensate it. What many people, I realized at help session did not get, that your heat pump should not work all the time. You know, it's enough to work several hours a day to compensate this heat loss. So your Q dot will be nothing, but it should be equal to this QH or Q out. Does it make sense? Now, what do you know in your problem? You know work input here, right? You know it's 8.5 kilowatt. So here is your equation. Here is your equation. What do you know in this equation? Actually, to be very specific, here it is. You have two signs of equal. So what do you know? You know work over cycle. You know this work input. And you know Q out here, right? It will be Q dot here. Q dot, Q dot, Q dot. Right? So what is required to find? You need to find this value and find how many hours you need to work. So key point is the following. It looks like you have one equation and too many unknowns, right? You know work over cycle, you know this one. What will be gamma? If you should read the text body. If it stated that you have Carnot cycle, then what? Then here is your coefficient of performance. You will get your temperatures in Kelvin scales. Make sure your temperature will be in Kelvin scales. Here is TH, here is TL, and then you know this value. So when you know gamma, you can find anything you need and calculate. Okay. Now, it was another question. What happened if instead of heat pump, you have just resistor, just electric resistor? What will happen? The answer is the following. What is good about heat pump? That you deposit work input, but it is QH or Q out which goes up. So we are lucky. So in fact, this coefficient gamma is larger than 1, so you deposit much more heat than work input. If there was no heat pump, if it was just resistor, then what will happen? You don't have the system. Instead of QH, you will have work input. So they should be equal then. So your efficiency will be gamma time less. And you will, how much money you will pay? You will pay gamma times more. Do you understand this? So instead of QH, instead of QOut, you will have gamma. If you did not fix it yet, please submit. Okay, I believe how the chapter 6 is done. So let me start something else. Let us proceed with something else. Let us do chapter 7. So here is chapter 7. So here in chapter 7, we will talk about entropy. And actually, we'll talk about entropy almost until Thanksgiving, and even almost until the end of the course. And this is difficult topic to understand what is entropy. So what is our point to do here? Our point, our goal here, we keep quantifying second law. You already know second law, right? You know what is possible, what is not possible. What does it mean when we start quantifying? It means that we found maximal efficiency that possible. But when your efficiency is less than maximal, remember, we say if you assume your efficiency is 60%, but your maximal efficiency is 60%, but your real efficiency is like 40 or 50. Do you see difference? Yes, we see difference, but how to quantify it? So that's what we are going to do. Entropy will be a way to quantify irreversibilities. The more irreversible cycle, the more irreversibilities you have, the more entropy will be generated, and the less will be your efficiency or coefficient of performance. Does it make sense? I hope so. So, and there will be some stage how I approach it. So I will approach, there will be 4 ways how I approach entropy, and you should understand. What are they? First, it's philosophical, that I tell you at the very beginning. Second law tells you something that nature does not want you to do, right? So nature does not want you to transfer heat from cold to hot source. Nature does not want you to convert heat into work, right? Why? Because it's against irreversibilities, because it's irreversible, because this is step to thermal death. And second law tells you, okay, if you want to do this, and that's what we are doing every day, you must pay penalty. Okay, you must pay penalty. And currency in which you pay this penalty is entropy. That's first approach. Second approach, you know, maybe from basic principle from school, from basic literature, that entropy is a measure of order or disorder, right? So if you, the more disordered your system, the more entropy you have. And actually today I send you a link, you don't waste time in the class, I send you a link about some nice MIT movie about the introduction into entropy. You realize that if you have system like soldiers are marching, they're ordered. If people are just walking in the street, they're more disordered. But if birds are flying, they are much more disordered because they're flying. So the more disordered system, the higher entropy it is. And you may realize that if you increase temperature, you make your system more disordered. When you pressurize your system, you make it more order. So your entropy, its measure of order and disorder should be function of pressure and temperature, right? That's second approach. Third approach. Third approach will be formula that we will show today. It will be formula how to calculate entropy. You can calculate it by formula. And approach 4, fourth approach, it's entropy, specific entropy. It's one more item in your tables. Remember your property tables. You have several columns, right? You have specific volume, specific internal energy, specific enthalpy, right? Now you have one more quantity named S. entropy. Okay? It will not be conserved, but it will obey some laws. So you should consider entropy just one more item in your table. And whatever you're able to do now with H, U, and V, you should be able to do with S, with entropy. So that is what is your task for the next week. You should be flexible with entropy. And all these four definitions that I give you, they coincide. We talk about the same item. So how to approach this? So I recall that there are three prominent formulations for the second law. We discussed Kelvin-Planck statement that the heat engine does not work with one reservoir. You must have second reservoir. And there is Clausius statement that your refrigeration does not work for free, right? It should work input heat. And third statement is entropy statement. And you know how it looked like? It stated that it is impossible for any system to operate in such a manner that entropy is destroyed. Okay? Look here, entropy is destroyed. It cannot be destroyed. Don't say, as sometimes people call it entropy increase principle, but don't say that entropy always increase. It is only isolated system where entropy always increase. In general, entropy can decrease. Entropy can decrease. So don't say entropy always grow, it's wrong. Like don't say for Clausius statement that you cannot transfer heat from cold to hot source. You can, you need to pay for this. The same here. Entropy can be generated from nothing, like a penalty ticket, but it cannot be destroyed. Imagine you are driving and you got penalty ticket. It's there. You didn't expect it, but it's there, you have it. And now you cannot destroy it. If you cut it, it will be worse. Even tomorrow and until after today you drive perfectly, you are a brilliant driver, you still have this ticket. You can destroy it. Does it make sense? Entropy cannot be destroyed. You should understand this. But if you talk about some kind of system, entropy can decrease. Why not? I will repeat it a couple of times. If you understand it from first time, it's great, but I want you to dive in this. Imagine I have glass of water or glass of tea. Let's say I put it into a fridge. What will happen there? It will crystallize, right? So what will be with entropy? Entropy will decrease, yes. Crystal structure of ice is much more ordered than liquid, and liquid is much more ordered than vapor. So I decrease entropy of my tea or water, whatever it is. I decrease it. But when I put into a fridge, my fridge generated much more entropy that I take out from water. So overall, entropy of the universe increased. Right? Another example. I take this glass of water and drink it. Glass of tea and drink it. So now I have empty cup. Definitely entropy of this cup decreases. But in my stomach now there is chemical reaction. There is many interesting processes in my stomach. So, and it will be very hard to get tea back from my stomach, right? So it will generate more entropy. Overall entropy of the universe will grow. But entropy of this cup decreases. So entropy can decrease. It cannot be destroyed, right? I can ask my friend to pay penalty ticket instead of me, so I get rid of it. But we cannot cut it, just cut it. So what is entropy? I'm talking about it. Let's try to introduce. And before it, we come back to Kelvin-Planck statement. And what Kelvin-Planck statement tells you? Kelvin-Planck statement tells you that it's alternate analytical form of the statement, that work over the cycle cannot be positive. It can be negative or zero. It is negative when you have irreversibilities present, and it can be zero only if you have internally reversible cycle. And that's understandable, right? That says is why you cannot operate with single reservoir. If you do it like this, it would not work. Because if you make your system go in counterclockwise, from clockwise to counterclockwise, this sign less than zero, this negative point will become positive, which is impossible. It's only zero, which is equal to minus zero. Does it make sense for you? I hope. I recall, chapter 6 and 7 has a lot of philosophy and a lot of difficult concepts. You may get stuck. But when you will understand it, everything will very clear and self-consistent. Mass, entropy, second law, everything will self-consistent. So please try to understand. we approach the same from different state points. So there is a concept in addition to Clausius inequality. Please don't confuse Clausius integral, Clausius inequality, and Clausius statement. In thermodynamics, there were not too many scientists who used to work. There was Clausius, there was Kelvin, there was Carnot, and a few others. So don't confuse Carnot principles and Carnot cycles. Don't confuse Clausius statement and Clausius inequality. So what is it? Let me drive like this. So let me consider a system like this. Let's say I have thermal reservoir here, okay? And I have a reversible, hypothetically reversible cycle here. This is power cycle. So you know that even reversible cycle does not work with one reservoir. So it should release some heat here. And let's say this cold reservoir is my system that I use. It will be real system that we use. So what I'm going to consider here, I'm going to consider my reversible heat engine and entirely my system with this reservoir. So what I will write down? First and foremost, this is closed system, right? There is no mass transfer. Let me write down here, what I write down, it's first law, right? In this small case. It's first law for a closed system. Do you see it? Yes. So it states that work over the cycle, it will be heat transfer minus dE. What happened? Tell me, please, what happened if I integrate this equation over the cycle? What will happen with me? You understand that what will happen with last hand side, with the right term? Right term will come to zero, right? Because E, energy over the change over energy over the cycle is zero, right? Energy is a constant. But work and heat, they are not zero, they will be finite value. And if I talk about reversible cycle here, I will have this relation. Remember that actually Kelvin principles, that for reversible cycle, we will have like this. Temperature is proportional to heat transfer. So let me substitute this equation here. What will I have? I will have like this, right? Remember, temperature here is in Kelvin, and we have this equation. Now, let me integrate this equation in over the cycle. What will I have? If I integrate, right-hand side will go out, correct? This will go out. So I will come to this equation. So look at this equation. Look what I have here. What do we have? We have that work over cycle is temperature and integral dq over t. Now let us discuss what signs do we have here. What is the sign of t? What is the sign of t? It's positive, right? At least it's non-negative. It's from absolute zero. It's in Kelvin. So t can be positive or it's zero. If it is zero, it means that you are at absolute zero, right? Now, what is this value? We just discussed that this value is non-positive, right? And in which case this value is positive? If it's not in negative, it's negative when you have irreversibility, and it's zero if you have internally reversible cycle. So what do you think about this term? If this is positive and this is non-negative, definitely you can write from here that what you can write the dq over t will be non-zero. And why I call it, that is Clausius inequality, and why I call it in brackets, inequality. Because for internally reversible case, it becomes equality. So if I have irreversibilities, I will have sign minus here. If I don't have, I have equality. dq over t is there. This is Clausius inequality. Please remember, it's an important point. Definitely in your exam, you may have a question like this. What is Clausius inequality? How it look like? Is it larger than zero or less than zero? How it look like in general? How it look like for Carnot cycle? How it look like for reversible cycle, for irreversible cycle, impossible cycle, whatever it is. Now, why I do it? So what do you see here? You have this term dq over t and you integrate. And now you see that what I have here, I have dq over t, it's some kind of quantity here, right? Can I take it like a quantity over this value? So why we do it? From here, can I define function like this? Can I define such a function that its differential will be dq over t over internally reversible process? Can I do it? And later you will see that it will not depend on trajectory. It will be property. Obviously, this unity will be like this. If I integrate it, its change between state 1 and state 2 will be this integral. The unit will be kilojoule per Kelvin, energy per temperature, the same like specific heat. So dimensions will be like specific heat. And if I take specific value, it will be dimensioned by specific by the kilojoule per Kelvin per Kelvin per mass per kilogram, like specific heat. But it's only dimension. In reality, it's not specific heat. It's completely new item. And this is a definition of entropy. Okay, this is the formula. So that is a definition of entropy. That's how we define. And later you will see, or you can believe me, that everything else I talk about entropy, that this is a property from your table and so on, it's exactly that one. So that's how we define it. Now, you should definitely define it with respect to some value, right? Because you say it's delta S. So what will be zero level? What will reference frame? So conventionally, reference frame is the following. We say that at absolute zero, entropy is zero. So at S tends to zero if T tends to zero. And this statement people call Nernst theorem or third law of thermodynamics. So remember, we already have fourth law: zero, first, second, and third. Zeroth law is concept of equilibrium, that you're in equilibrium with somebody if you have the same temperature. First law is energy conservation. Second law we are talking about for a while now, and third law that entropy should tends to zero at absolute zero. Okay? Does it make sense? Okay. Now let us postpone entropy for about 10 minutes, and let's keep talking about what? About Clausius inequality. Why do we need it? There are some interesting things to say. So from Clausius inequality, there is a concept of Clausius integral. So this is this value sigma, and we define it like this, that sigma is minus this integral. This integral is taken over boundary condition, dq over t along the boundaries. Why it's minus here? Well, I don't like it, but it's conventionally. Conventionally, this you have sign sigma, you have sign minus here. That is Clausius integral. So its integral is performed over all parts of the boundaries over the entire cycle. Subscript B means boundary. Okay, and then you may see from here that if you have irreversibilities, what does it mean? This means that this integral should be negative. Remember from Clausius inequality. So sigma will be positive. If you don't have irreversibilities, this should be zero. It will be Clausius equality, and sigma will be zero. And finally, if occasionally your sigma becomes negative, it's impossible. So when you look here, does it resemble you something? Is it similar to something you did by today in the homework? Yes. That's how you identify nature of the cycle. Reversible, irreversible is impossible, right? Remember what we did. You identify, say, thermal efficiency. You identified Carnot thermal efficiency and compare, and made conclusion. Is it possible, impossible, or reversible, irreversible, right? But there is all the same for coefficient of performance, for gamma or beta. But you can do exactly the same. This is the second scenario how you can do. You can calculate this integral and see if it's zero, you will say, okay, it's irreversible. No, it's theoretically possible. If it's positive, that is a measure of entropy generation. It's a measure of irreversibilities. It's a measure of penalty you pay. If you drive ideally, you don't have penalty ticket. But if you do something wrong, how it practice, you will get your penalty. So your sigma will be positive, you cannot get rid of it. But sigma cannot be negative, right? You don't get bonus tickets from police officer if you drive very well, right? Unlike our class, you don't have bonuses for best driving. So that it is. So look here. Read the problem here, and you remember this problem? We solved this example in previous chapter 6. So let's say I have a cycle, heat engine. My cycle receives 1,000 kilojoules by heat transfer from a hot reservoir of 5,000 Kelvin and discharge 600 kilojoules to another source at given temperature to be 200, 300, 400. And we describe what is the nature of this case. So how we did it that time? I come back to slides of chapter 6. Here it is, right? So basically that is a problem, right? Remember it? So we have hot reservoir. Here you have 1,000 kilojoules goes here. 600 is discharge. So, and that's what we solved. So what we did? We calculated your efficiency, which appear at 40%, and then you calculate maximal possible efficiency based on temperatures and compare. Do you know this? You must know if you submitted homework number 6. If you don't know this, you're in trouble. So how we did it? First, you calculate your efficiency, get 40% here, and then you calculated maximal efficiency for 3 cases. You get 0.6 if TL is 200, with the conclusion that, okay, theta is less than maximal, so it's irreversible cycle. If TL is 300 Kelvin, you come to conclusion that theta is equal to maximal, so it's theoretically possible and reversible. And eventually, if your maximal efficiency is 0.2, it's 20%, you come to the conclusion that it's impossible, right? Everybody remembers this? It's trivial for everyone? Okay, now I show you how you can solve it in different manner. You can do exactly the same by calculating sigma, Clausius integral. Calculate sigma and see, is it larger than 0, less than 0, equal to 0, and make the conclusion. So here is it. So this is your sigma, you calculate it like this. It will be Q H over TH minus QL over TL, right? Don't forget about, so key point, don't forget about sign minus, and don't forget that your temperature should be in Kelvin. Like in chapter 6, it's classical mistakes, and I do believe like 10% of you will do this mistake in your exam. You will take temperature in Celsius and you will get absolutely wrong item. You understand? Imagine temperature is the street in -5 degrees Celsius. It will be soon like this, nighttime. So will you get negative efficiency? No, you must calculate from Kelvin. Anyway, so now let's say my TH is 500, TL is 200. So what we will get? Based on this, you calculate that your sigma is -1 kilojoule per Kelvin. Again, how much is here, it does not matter. It's the key point is the sign. -1 or -100, and you make conclusions that sigma is 1 kilojoule per kilogram. It's positive, so irreversibilities will be here. It's possible and reversible. Is it the same answer as we get before? Yes. Make sure it's the same answer. If it's not the same answer, something goes wrong. Now, let's say TL is 300 Kelvin. Then what I will have? That my sigma will be 0. What is the conclusion? What would be my conclusion? That this cycle is reversible. No irreversibility is present within the system. Finally, if my temperature TL is 400 Kelvin, I will count that my sigma is negative. Don't confuse the sign, it's negative. And then it's impossible. Exactly the same conclusion as before. Now, I tell you about signs that you consider here. So here you say that it's impossible because sigma is -0.5, right? If sigma is -0.01, it's still impossible. And if sigma is -2000 of some units, it's still impossible. You cannot be partially pregnant or partially dead. Either dead or alive, right? That's a story. If it's less than 0, it's impossible. It does not matter how small. Police officer will never give you bonus tickets for driving, even small one. The same story here. It's possible, it can be 1 value here, it can be 20, it can be 100, it can be 10 to the power 10. It means how ineffective your system. Your sigma is a measure of entropy, it has dimension of entropy. It's a measure of irreversibilities. So the larger it's a measure of your non-idealities. The larger the sigma, the worse your system, but it exists. right? Do you understand this? So in the future, and while you deal with this study, I recommend to consider both examples, both options. Consider this way and consider this way to calculate, and make sure they give you the same answer. And in your homework that I gave you right now, there is problem number 3 in problem 7, in homework 7a. When I ask you to employ both methods, not one, both methods, and make sure you get correct answer. I tell you, homework 7a is quite comprehensive. There are many problems there to solve. But I do believe you should be able to deal with it. That is something that you. So your task is to deal with entropy, and you should be able. So by the end of this semester, the end of this week, actually, you should deal with entropy like you deal before with enthalpy and other parameters. And realize so now realize the following: still, chapter 3 is your backbone. Still, you need to know everything we did before. And if you look at the problems I gave you now, many problems look like before. It was like problem like you have a turbine which operates in some reversible cycle. Find for work output. So first question will be find work output. So it's like a problem from chapter 5. But there will be another question. Find the entropy generation. And it means that you need to employ second law. Also, some of the problems you will not be able to solve some of the problems we consider here last months because we will need to employ some knowledge about entropy. For instance, if you will talk about isentropic condition, that helps you to connect state 1 and state 2. But otherwise, again, we use turbines, we use compressors, we use piston cylinder assemblies. So it's exactly like it was before. I will send you basic equations, a balance equation describing entropy. Entropy will have balance equations. The only point that unlike mass and energy, entropy is not conserved. There is a source of entropy. But you should be able to employ it. Why I say this? Because some people will ask, what about chapter 3? So if you don't get what I'm talking now, it's bad. And if you did not pick up entropy, but you were excellent until exam 1 and 2, you have some chance to survive. In the final exam, you can get C, for instance, because you will solve some problems and some part of the problems. But if you don't understand how to use property tables, you will get F because you will not solve any single problem, and including chapter 7 and including chapter 6. Do you understand? So you are still, it's a spiral-like study. We start from the core and go around. You need to know property tables, please remember. So what about entropy? Now I want you to justify here that entropy is a property. So how we define entropy? We define entropy as change between states. So let's say it like this. Let me say I consider 2 internally reversible cycles. I go from state 1 to state 2 through a trajectory A, and then go through trajectory C. It's one cycle. But I may have another option. I can go through trajectory B and then go back through trajectory C. It's another option, right? So let me write down what will be with sigmas. What will be with Clausius integrals here? Let me see here. It's internally reversible process. So what does it mean? That I can go clockwise and I can go counterclockwise. It will mean that entropy should not generate in the cycle. It will mean that my sigma over cycle should be 0, right? So how I can apply it? So I go through boundary conditions and I will have. First I go through trajectory A and then through trajectory C. So I will have this integral and this integral. And altogether this should give me 0. Why? Because it's internally reversible. I go like this and then back. This is first line. And then second line. I go first through trajectory B and then through trajectory C. Again, I will have the same answer. Look at this equation. So what do we have here? I have that A, let me say like A plus C is equal to 0. And then I have B plus C is equal to 0. What can you say about A and B? What can you say about these two? These are equal. These are equal. So what about them? Exactly. They're equal to. So It's like this. That's what I have. And so what does it mean? It means that when I go from state 1 to state 2 through trajectory A and trajectory B, I get the same answer, right? It will mean that my walk, my path, my track from from 1 to 2 does not depend on trajectory. True? What does it mean? It means that this quantity does not depend on trajectory. It depends only on difference between state 1 and state 2. It means that it is a property. The same property like energy or mass or volume or others. It happens that it's a property. Remember, the quantity is a property only if it's changed between two states, it's independent of the trajectory. Otherwise, it will be path function. Heat and work are not properties, but entropy is a property. And that's why it is in your tables. And again, you will see that entropy is additive value. So that's it. It is, so it's a property. You calculate it in a slow internal reversible process, and you will see that if you divide it by mass, you will have specific entropy. So what we will see about that it is. And now you will see that since entropy is property, you should not care if it's internally reversible or not. Because you have state 1 and you have state 2. Somebody give you entropy at state 1. Somebody give you entropy at state 2. So difference between these two states will be S2 minus S1. And it does not matter how you go. It's a property. So let us summarize. This is entropy trivia. So entropy, what is this? So you remember, somehow entropy resembles mass and energy. So entropy is extensive property. So if you divide your system by 2, entropy will be divided. It's associated with specific values, right? Again, it will be balanced equation for entropy. But unlike mass and energy, entropy will not be conserved. There is no entropy conservation. There is a source of entropy, right? When you get a penalty ticket from a police officer, it looks like this ticket appeared from nothing, from never. You just drove and now it's here. It happened. Okay. How we come to balance equation? Exactly like before, like mass and energy, entropy can be transferred through the boundaries by mass, by work, by heat. But also it can be generated from nothing. It's like we discussed, it's extensive. And one more thing I want you to realize here. Entropy, so entropy itself is positive, right? It's because it's your penalty ticket. Your penalty ticket cannot be negative. Nobody will tell you that go and get money for your best driving. But entropy change between state 1 and state 2 may be positive, maybe negative, maybe 0. If it's 0, we call it isentropic process. That's important point to realize. If it's 0, because like I described, when I put a cup of tea into a fridge, I decrease its entropy. It may go down. Or on the other hand, if I heat it, I increase entropy. I may have isentropic process when it's 0. It's okay, right? So, and the entropy increase principle says that entropy cannot be destroyed. It does not say that entropy cannot decrease. It can decrease. It cannot decrease only for isolated system like our universe. Entropy of the universe goes up. And any thermodynamic action we make, it's step towards thermal death of the universe. Again, by units of entropy are exactly like for specific heat. Specific entropy will be like value R, it will be kilojoule, kilogram Kelvin, like Cp and Cv. Okay, so now let's arrive to entropy increase principle. That's actually entropy statement of second law. So it's like this. Now we will derive and understand. And please pay attention to what I have in this slide, because you will realize, well, it may look trivial, but it's not trivial, it's something important. Please follow me, because I will tell you something interesting. So let's say I go from state 1 and state 2 and then back. And let's say process 1, 2, which is shown here by dashed line, it's like arbitrary process, which is reversible or irreversible, some kind of process. But process 2, 1, it's internally reversible. It's solid line. By the way, by convention, here in your textbook, and I follow this convention, solid line will show reversible, internally reversible processes, while arbitrary realistic processes will be shown by dashed. I don't like it because, like from geometry, from typically what we say, typically dash shows something imaginary that you don't see, right? While solid shows something visual. Here it's vice versa, because irreversible cycles, that's what we have in reality. Reversible is some abstractions that we don't have. But that's conversion, so let's follow. So let me write down Clausius inequality. Here it is, right? So here is my Clausius inequality for this cycle. Okay? And I can definitely split it like this. I can write it like, first I go from state 1 to state 2, and then I go from state 2 to state 1 through internal reversible process. But what do I have here? Do you see here? What I have here? This is nothing but definition of entropy change, right? Which drives me here to this, which drives me here to this expression. So I will have dq over t, it will be s1 minus s2. And what I will have from here? I will arrive that s delta s, s2 minus s1 should exceed this. Or if I take integral, I will have that s2 minus s1 should exceed this value, right? Should exceed this. Now, let me say, when I say exceed, so it will be that ds over d2 will exceed this integral. Now, when I say exceed, what does it mean exceed? What does it mean that I am larger than you? Let's say like, or vice versa. Don't be offended. What does it mean that I'm larger than you? What does it mean that A is larger than B? It means that A is B plus something, which is non-negative, right? If I'm larger than you, it means that I am U plus something which is positive, which is non-negative. Do you agree? So then I can write like this. I will write that S2 minus S1, it will be what? It will be integral. What does it mean that S2 minus S1 exceeds this integral? It means that this is integral plus something which is non-negative. Okay? And this is something what we will call entropy generation, entropy production. This term is entropy production. Please understand, it looks like trivial, but it's very philosophic point here. What I say here, I say that my entropy change, it will be integral like this, plus entropy generation. And this is entropy balance equation. I simply say here that my entropy change exceeds this integral. Which means that it equals to this integral plus something, which is non-negative. And you can see here, okay, what happens if I have internally reversible process? If I have internally reversible process, I simply have that there will be no entropy generation. This will be internally reversible like here, right? Internally reversible. And I will come to definition of entropy. S2 minus S1 is dq over t internally reversible. By default, it's like this. But if I have realistic system, then it's not the case anymore, and I do have entropy generation. Do you understand? That it is. Now, and now I can formulate my entropy increase principle like this, that entropy generation is non-negative. Entropy generation should exceed zero. It's like this. This is entropy increase principle. So statement that I just told like this is entropy statement of the second law. Entropy cannot be destroyed. Entropy generation is non-negative. Okay? Don't say that entropy goes down. Entropy cannot decrease. Entropy cannot be destroyed. And of course, you realize that entropy, you remember we talk about internally reversible and externally reversible process. So generally speaking, entropy generation is total change of entropy in the system and out of the system. What it means here? So when I put T into a fridge, entropy of T decreases, but fridge surrounding generates much more entropy than it decreases here. So total entropy of the system fridge plus T increases. Entropy of our universe increases. The same story, when I drink tea, entropy of empty mug decreased. but entropy of my generated in my stomach increases and dominate over that. So totally, me plus cup has more entropy than before because you cannot get tea from my stomach back in previous condition. Do you understand this? Does it make sense? Again, so that is what you see here. 2 points: entropy increase principle. Here it is, and that for isolated, it's only for isolated system that entropy grows. If system is not, remember, isolated when there is no energy transfer. It's not closed for sure. Yeah, isolated is closed, but closed system is not isolated because it can be energy transfer. So overall, if your system is not isolated, entropy can decrease. Either it's a closed or open system. And we see here that entropy is additive value. So total entropy of big system is summation of entropies of subsystem, as it should be. Do you understand this? So that are some remarks here again. So entropy generation is positive. And here, that is exactly example of what happens if I put vessel into a fridge. Here you see it. It's stated that, for instance, water gets frozen, so its entropy decreases by, let's say, 2 kilojoule per Kelvin. But your fridge generated 3 kilojoule per Kelvin. So total entropy generation is positive, as it should be. Otherwise, this process may not work. A process that violates entropy increase principle, that entropy generation is non-negative, does not work, it's impossible. I recall, since we have entropy generation, entropy is not conserved property, and there is no conservation of entropy. There is entropy increase principle, but there is no conservation. Entropy is conserved only in idealized reversible processes, which we call isentropic when entropy is constant. Otherwise, it increases for all actual processes. And entropy generation is a measure of irreversibilities. It shows how non-ideal your process is, how much penalty you pay for this, right? And the last point I show you here, that basically entropy, it's the item from your tables. Remember your property tables? Remember how I started chapter 3? I told you that there was example, the properties associated with superheated vapor in table 6. Let's say I have 10 megapascals and 400 degrees Celsius. Here is your table, right? So remember, it was temperature for given pressure, and you say, okay, here is your specific volume, V, here is your specific internal energy, U, here is your specific enthalpy. Don't confuse enthalpy and entropy, two opposite items. And now you have one more item to deal with, it's entropy. And everything you did with V, U, and H, you should be able to deal with S. All formulas, all diagrams, remember TV, TH, PV, pH diagrams, and so on. Now it will be TS diagrams and others. Remember, if you have saturated mixture, how you calculated U and V, you take this formula, right? Now it will be exactly the same formula for entropy. If you have saturated liquid, it can be approximated by the property of saturated. If you have subcooled liquid for given pressure and temperature, it can be approximated by the properties of saturated liquid at this given temperature. Do you remember this? Now it's the same for entropy. These are, remember all these plots? This is classical TS diagram. It's very similar to TV and TU diagram. The same bell here, the same critical point, saturated line, saturated vapor. Exactly everything we did before, you have here. Compressed liquid, superheated vapor, saturated liquid vapor mixture, exactly TS diagrams as they are. Total entropy change, it will be M delta S. I will stop at this point, exact 50 minutes. So say I will stop, thank you, and please submit your homework if you did not yet homework 6, and please take seriously chapter 7. I am ready to answer your questions. And also I will pause this lecture and I see you on Friday. Thank you. Let me stop sharing my screen and let me stop recording.